Hey guys, how's it going? Welcome to the next section of the series. We are going to start exploring liquefaction mitigation and seismic resilience. This is going to be a little bit more of like a technical thing because, Wednesdays. But in either case, we're still going to be explaining it in a way that's easy to understand, I guess, right? So I'm excited to jump into this. We're going to be talking about liquefaction. So liquefaction is still a relatively undiscovered phenomenon, not in that we don't know it exists, but only that there's ongoing research in the geotechnical community and no specific standard set of testing or anything like that specifies what or how or why to identify and treat liquefaction. There's several different mitigative techniques for liquefiable soils, and there is several different ways to identify liquefiable soils. So it's an ongoing discovery process in the geotechnical community. It's a lot of fun, right? It really garnered a whole lot of attention once some major damage from liquefaction was observed in Japan and Alaska back in 1964. It's been around since the dawn of time, right? But since then it's gained worldwide attention. Or since it has gained worldwide attention, the effects have been noted throughout all of history, right? There were some earthquakes back in the really early 1900s, late 1800s, that had damages that were liquefiable soil damages, but it wasn't known at the time, so there wasn't a whole lot of testing that was done. It was kind of like an opportunity missed, but really it's kind of since 1964 on, it garnered a whole lot of attention, and the geotechnical community's been really, really excited about this stuff, and so am I. I was introduced to liquefaction from one of my previous employers, and it really, really, really piqued my interest. So it's something that I've been diving into, not just in relation to what we do with it, but really all of the mitigative techniques and identifications. All this is really, really fascinating stuff. So, in 1971, there was some slumping that was due to liquefaction that nearly resulted in the overtopping of a dam down at the bottom of the LA aqueduct down in San Fernando Valley. If that occurred, there would have been flooding for thousands and thousands and thousands of homes back in 1971. In Christchurch, New Zealand, 2010, 2011, there was a sequence of earthquakes that happened, destroyed 15,000 homes, and also leveled several buildings in the central business district out there. And the city of Japan, Kobe, Japan specifically, is still trying to recover economically from some of the liquefaction-related damages that happened during the 1995 Hyogogen earthquake, or Hyogogen Nanbu earthquake. Sorry, I'm trying, man. So the big question, really, I've got some notes over here. I'm sorry, that's why I keep glancing over here. So the real question is, what is liquefaction? So liquefaction is the stress and deformation which disturbs the soil structure. Generally a sandy soil, right? And generally due to ground shaking, and ground shaking is generally caused by earthquakes, right? I know everybody was waiting for that. Anyway, stress and deformation disturbs the soil structure in generally saturated, geologically unconsolidated fill soil, right? Happens a whole lot in sands, or it's a lot more common in sands, but can happen in some clays and silts and some other stuff like that. What happens is during the moment of ground shaking, water in the pore spaces of the soil generally has the tendency to resist consolidation, right? This is why you have strength of soil while it's in situ. But soil can't change in volume until the water is released from those pore pressures. So what ends up happening is during the ground shaking moment, the pore pressure rises, those soil particles lose contact with each other, and then the entire soil mass ends up losing strength. By losing strength, I mean it turns into a liquid muck. As the name liquefaction would suggest, it liquefies. So you had imagine having a building that's sitting on top of strong soil, and then all of a sudden that same building is sitting on top of water. What do you expect happens, right? Anyway, so this process where the ground shaking shakes up all the, disturbs the soil and messes with the mass, and you blah, 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 that's called liquefaction triggering. And there's a lot of different ways to test for that, okay? And we're gonna get into that in a different video. That's not what this video is about, but that's called liquefaction triggering. The phenomena that occurs in the soil during the liquefaction shaking is called flow liquefaction. However, most of the time when people say the word liquefaction, they're generally using it interchangeably between liquefaction triggering and flow liquefaction. They're talking about both at the same time, right? So that's sort of what it is. The types of damages that can occur from this are just massive, right? I strongly encourage you guys to check out some of the stuff that's on the CalGeo website as far as like the Christchurch, New Zealand earthquakes, or just run a Google search and jump into like images and stuff like that. I'm going to refer to them during this explanation here, but strongly recommend you check it out. Really cool pictures. Yes, a lot of damage, a lot of destruction, a lot of stuff like that, but really cool pictures and ultimately very informative, right? That's the word I'm looking for. So anyway, ground displacement. This can be vertically or horizontally, right? Absolutely can trigger landslides. Okay, we were talking about that San Fernando Valley, LA aqueduct embankment slump, right? So the embankments that retain water can begin to slump, and if that begins to settle down, it can get water flowing over the top, and it totally defeats the purpose of that embankment that's supposed to be there, right? Foundations, and I don't mean like necessarily structural foundation or like foundations of a structure, but any and all foundations can begin to fail. Foundations fail. Can begin to fail, right? And one of the cool things is that mixture of soil and water, a la mud, right, pushes to surface. So this is one of the phenomena that's really kind of, it's not isolated to liquefaction, as I just heard about what a mud pot actually is, which is more volcanic activity, unless you're talking about the one down in San Diego, El Centro area down by the 8 freeway. That's not volcanic related, that's more like seismic related, but in any case, when the soil mixes with the water and it liquefies, the pore pressures are all increasing, the water has a tendency to rise. So what can end up happening, which you'll see in a lot of the photos of liquefiable damages, is that there's this mud that comes up to the top, and everything that you would have been walking on is just this nasty muck, right? And also cars sinking into said muck, because muck has no structural integrity right when it shows up. So these are all ground displacement, landslides, embankment, foundations fail, soil and water can push to the surface. We're not done. I just ran out of room. So sinkholes. They can either form or they can open up, right? Settlement, distortion of what? And collapse of buildings. Told you in Christchurch there was 15,000 homes that were damaged by liquefiable soils conditions, and several commercial buildings in the central business district that wound up completely failing, right? It's a nightmare, right? So disruption of roadways and failure of earth retaining structures. Failure of retaining structures. Yes, I'm reading down a list because it's just easier for me, right? Cracking, sliding, and overtopping. Cracking, sliding, overtopping of dams, embankments, reservoirs, right? Other earth-related structures or structures that are designed to retain water back, right? Severing or rupturing, sewer, water, gas lines. You can imagine with all the soil moving around and lose structural integrity, plus the shaking, plus all of the loads that are on top. So I'm going to talk about this in a second, but how the load transfers from those soil particles into the water that's in the pores, right? How that happens and is shaking everything up with all the utilities that are underground could potentially create a whole lot of damage, right? Lateral displacements or shear failure of caissons, right? Piles and underwater piles, caissons, piles, whatever. Anything that are supporting bridges, right? Get that, and uplift of underground structures. So underground structures that have like all that water rising, you've got all that mud that's pushing up and creates a lot of upward pressure. Once again, you run that Google search, you're gonna find Christchurch, New Zealand, and they've got pictures of like sewers that are picked up out of the ground, right? So it's devastating, yes, and it's also very fascinating, right? So these are all very, very serious damages, and that's why City of Kobe had such economically like damaging times when they had that had the earthquake over there. So it's just something really you want to pay attention to. You can see the necessity for identifying liquefaction, triggering or flow or whatever, and mitigating it. You know, before an earthquake or some seismic event liquefies the soil and takes out, let's say, a hospital, right? So actually had the pleasure of looking at a hospital one time that was being designed over liquefiable soils and putting like 1,200 piles as a part of the foundation system, and that's one of the mitigative things that could happen. If you had a shallow foundation system, just because you're not on a hillside and it's flat land, but you're sitting over liquefiable soils, then you have a very, very dangerous situation that it can be in, right? So you can see all of the damages that are potential and how dangerous the entire situation can be for liquefaction. So what exactly is it? I'm going to draw you a quick little graph. I'm so sorry about my drawing. I'm going to draw you a quick little diagram or figures to show you what it is. And I really want you to pay attention to this diagram because it's going to become it's going to become a central part of what we talk about later with like the testing, with what we're doing, how this thing works, et cetera, right? So I really want you to pay attention to this diagram and put it in the back pocket. We'll talk about it later for sure. We will absolutely be referencing it several times. So what we have is a volume, and I'm gonna shorten it for one. A volume, okay? And we're gonna pretend that these are all the same size because I can't draw. All right. We're gonna pretend those are the same, okay? So what we have in a standard type condition, in a standard condition, you see that the soil particles are chilling here, right? The surface loads pushing down on here are really transferred between the soil skeletal structure. So this connects, these are all interconnecting, and they're carrying the load down into the soil and displacing everything down at bottom, right? Or it reduces the load down at the bottom. In between, you still have all of the moisture and water and pores of that skeletal structure, right? So that's what happens. So what ends up happening during liquefaction is the ground starts shaking, right? And it disturbs this cool little soil skeletal structure. What ends up happening is temporarily at least, you can see that there's no more connection here, right? These are no longer bridged together. So the volume can't change, right? The volume of the soil can't change until the pore pressure until the moisture inside the pores pushes out or expels or increases or whatever else. So the volume can't change. You're in the same little diagram. It's actually technically the same number of dots over here. I just suck at drawing, I'm sorry. But what ended up happening is the loads that are pushing down here is now more onto all of that water inside the pores that was mixing up with everything, right? Boom. So all of that load is being transferred through something that doesn't necessarily have a lot of strength. When you're here, you got that skeletal structure of the soil particles. You can carry all the load and transfer everything down. It's just like a house, and you can follow those loads down, right? It's the same thing, and this will resist downward movement. Now, while this has the tendency to resist downward movement, now you're moving the soil particles. And what ends up happening is you shake it all up like it's in a blender, right? And then at the very end of the day, what you end up with is another soil structure where they're all connected, right? So all the load is still here. I'm sorry, it should be the same amount of circles. I just suck at drawing. But these are all interconnected, right? So you end up with a very strong, very dense thing here, but what you also end up with is all of your moisture up here. Where's the water gonna go? Or where's the load gonna go? It's gonna go into the muck, right? The sinkhole, the void, through into the liquid, the mud that you have that's trying to support the structure or whatever, like that's what's gonna try and support the loads on the surface. And then you get to the structure as it settles down into the below, something that's actually stable, right? So that's why you have expected settlement or target settlement or all that fun stuff when you do the design before and after testing on liquefiable soils conditions. So this is what liquefaction is. Relatively solid, ground shakes, mixes it all up, turns it into liquid, right? Expels the water in an upward thing, reconsolidates, and then happens here. This is triggering and flow liquefaction, both the phenomena at the same time, right? So again, I want you to pay attention to this. This is going to become important later when we start talking about how to mitigate this. I do intend to explore as many different mitigative techniques as I am familiar with, and I'm also still researching it so I can talk educatedly about some of the other methodologies that are highly successful, right? My goal is to bring to the table just very, very successful things that are either written into the building code or have the proper testing that we were talking about last time in order to complete sort of this liquefaction circuit. My goal is not to tell people how to design it, nor is it to help them bid it or anything else like that. No trade secrets going on, nothing else like that. I also plan on referencing a couple different pieces of research material, some things that are published on CalGeo website, which makes it public domain, which means technically I can talk about it, but people technically don't want me to talk about it, which I don't know why it's not in the interest of the community, but mumbling. Hopefully this is informative for you guys. We're gonna build up on this. I think next time we're gonna talk about some of the testing methods that you can do to identify liquefaction triggering things. Awesome. We talk super educatedly and end it with the word things. It's good. In either case, thank you guys so much. Any questions, comments, concerns, drop a line below or message me privately. Please like, subscribe, share, and do all that fun stuff that people do for online presence. Thank you.